Okay, welcome back. This is now 2.4, and basically applications uh, of the kind of analysis we've been doing to digital logic circuits. So somebody probably from MIT realized that there's kind of a one-to-one correspondence between digital circuits and these truth tables and stuff like that. And we could use truth tables and equivalent statements and even, I guess, probably arguments, and maybe not. But you can use all of the tools that we've been developing in sections 2.1 to 2.3 in order to work with circuits. Okay. Circuits are on or off, and that corresponds to true or falses and that sort of idea. So anyways, let's get in here and take a look. 2.4 applications. And in particular, we're working with circuits now. And we can draw kind of a simple circuit diagram, which I'm sure they show you in the book. Let me get my book sort of open here. Yeah, so we have switches in series in this case, and I'll show that. So we have some sort of battery here, and you can think of these lines as wires from the battery. And then over here we have some switches, and they're in the open position right now. Okay. Let's try this over here. And right here we have a light bulb of some sort. Okay, so this is a series circuit. And the only way for the light bulb to work is both of these guys have to be closed, right? So we could do a truth table to represent that. So we'll call this guy right here P, and this part right here Q, and consider what happens to the light bulb when P and Q are open or closed. Okay, so all the different variations then are just like the true, true, false, false thing. So we'll say closed, closed, open, open, and then we have closed, open, and then the bulb, how does that work? Well, both of these have to be closed for the bulb to turn on. So the bulb will be on in this case, and then it'll be off in every other case because the electricity won't be able to jump over this open region here. This, you have to imagine, you know, this is the open position. The closed position would be taking this little lever thing here and pushing it down. And then you would have a complete circuit, and the electricity would be able to sort of cross over. Okay. Okay, so the only case where it's going to work is when both of these little switches are down in the down position. So it's this case. And the other case is no. It'll be off, off, off. Okay. So what sort of simple connector did we have that worked in this form? How does this correspond to truth tables that we've seen before? It's P and Q. It's a conjunction. Okay, so P and Q. So when you have a series circuit, you're talking about ands or conjunctions. And then when you have parallel, and they show a picture of that in the book, I'm not going to draw it out, that would be an OR case. Okay, so again, you can make a direct connection between everything that we've done in logic up to this point and circuits. Okay. Okay. So digital logic circuits. Okay, so you're going to have some sort of black box. And then you'll have some inputs into that black box, and then you'll have some sort of output. Okay, so the inputs will have P, Q, R, and then the output in this case we'll call S. So these will be our inputs, and over here the output. Okay, and then this black box can be any way you want to build it. We can describe it with truth tables, and the fundamental building blocks of these circuits, we'll call them gates. So those will just be the ands, the ors, and the nots. Okay, so fundamental black box circuits or gates, if you wish. Fundamental black box circuits or gates. We'll have zeros and ones instead of trues and falses. And we also have little pictures associated with these things. So for example, P, and then this symbol thing, this caret thing, that's the NOT gate. Okay. And then we'll have a corresponding table with it. So P, and then instead of trues and falses, we have ones and zeros. So when you input a 1, the output will be 0. When you input a 0, the output will change to 1. Okay. So this is the input-output table. Okay. The other ones, then the OR and the AND. So let's look at those. So I guess AND first. So P, Q, we have these inputs, and it looks like this. It's rounded. And then we have our R. So P, Q, R. And you get 1, 1, 0, 0, 1, 0, 1, 0. And it works the same way as it did before with the ands. They both have to be true for this to be true. So they both have to be 1 for that to be 1. And so it'll be 0 in all the other cases. The last one then is the OR. Okay, so you'll have this symbol, kind of like this, and then the output there. Okay, so P, Q, and R in our table. It will be 1, 1, 0, 0 as usual, 1, 0, 1, 0. And then if either one is 1, this guy, the output is 1 as well. So 1, 1, 1, 0. Okay. Okay. So the first kind of problems you're going to get in WebAssign, and if you're doing the book problems, the blue problems, if you do those have the solutions in the back of the book. So I usually just focus on those. But in the beginning, what you're just doing is given some inputs, some on or off, so some ones or zeros, you have to find the output for given the diagram. So section 3, finding the output. Okay, and we'll look at, let's make sure we got the right number here. Yeah, so number 1. And the book is nice enough to kind of tell you what the gate type is. They put the NOT inside and the OR inside. So it's not like you have to memorize what the little shapes mean or anything. So anyways, number 1, we have inputs P, Q, and then Q has a NOT gate. And that goes to an OR gate. Okay. And then it goes to R. So they're going to tell you what P and Q are. So in this case, P is 1, Q is 1, and then you have to determine what R is in that scenario. And you could kind of write in what each one is. So P is 1. Q initially is 1, then when you go through a NOT gate, it'll turn to 0. So you have 0 going into this OR gate. and then 1 or 0 for ORs, that's going to be 1. So the output will be 1. It'll be on. Okay. Let's look at number 2. A little more complicated, but no big deal. These are pretty simple. Once you get the hang of it, it's like riding a bike. You're not going to forget how to do it. So we have P, and then an OR gate, and then we have a Q, and then leeching on to the Q is this wire going to a NOT gate, and then we go up here, and these are going into an AND gate, and out to R. And so the inputs here this time, P is 1, Q is 0, and then R is what? Okay, so P is 1, Q is 0 here, and it's also sending a 0 to here. And once it gets here, it's a NOT gate, so it'll change it to a 1. Here's an OR gate, so 1 or 0, that'll be 1, it'll be true. And finally an AND gate with 1 and 1, that'll be 1. Okay, so at the end, you get an output of being on. Okay, we want to be able to convert from tables to symbols to diagrams. And so they'll spend some time working through those kind of problems with you. Let's take a look at going from a circuit diagram to an input-output table. So section 4, we have a circuit diagram to an input-output table. Okay, so number 6, I think. Yeah. So they want you to use the diagram and figure in problem 2. That's right here. So let me draw that. P, we have Q. These are going to an OR gate. And then this is leeching on to a NOT gate. And then both of these are hooking up on an AND gate. And then it's leading to your output. Okay, so we want to transfer this into basically our truth table, but now they're calling it input-output table, right? So we have P, we have Q, and then we have our output R. And you could literally just do it brute force and consider all the different kinds of permutations of inputs. So we have 1, 1, 0, 0, 1, 0, 1, 0, and then trace out the different input-output values like we did in the previous 2 problems. Okay, so if you have 1, 1, we already, well, which one did we do already? We did 1, 0. That gives me an output of 1. Okay, 1, 1. And let's just remind ourselves, this is an AND, this is an OR, this is a NOT. Okay, so if I do, maybe we do them in like different colors or something, I don't know. Yeah. All right, so if I have 1, 1, how's that going to work? So I have a 1 going to this NOT gate, that'll become a 0 here. If I have an OR there, that'll be 1, and with 1, 0 will give me a 0. So that guy will be 0. 0. And then let's do 0, 1. Okay, so instead of that, let's go 0 and 1. So 1 here will go to 0. 0, 1 will be 1 again, and so that output will be 0 for an AND. Okay. And then let's try 0, 0. So this will be a 0 going into here, and then its output, when you negate it, it will be a 1. The output of an OR with 2 zeros is 0. And then finally, again, this will be 0, because you need both 1s for that to be 1. Okay, so that would be 0, 0, 0. Okay, so that's one way to do it. Let's look at a different type of problem now. So now we want to go from the circuit diagram into a Boolean expression. Because if you know that this black box, sort of this black box thing here is just P, the negation of P and, or rather the negation of if P then Q, then figuring out this last column is just as easy as negating that. You know, if P then Q is 1, 0, 1, 1, if you negate that, it's 0, 1, 0, 0. So you don't have to go through the piece by piece analysis, right? So in that regards, it simplifies things a bit. Let's look at an example from the book, though. Okay, so in particular, we want to look at 2.4.3 Part A. And this time what we're doing is going from a diagram into the Boolean expression. Okay. Which is basically just the compound statement. Okay. Or the compound, the statement form, which is just a bunch of variable statements and connectors. Okay. Okay, so the diagram given in the book, I'll reproduce it for us. So I have P, I'm going to a not, and then going to an and then a Q, going to an and then also a not, sort of attached on down here. Then we're going to an or, and then we got our output. Okay. Okay, I want to go from this diagram into a statement form, or as they're calling it in this new context, a Boolean expression. And so let's take a look. So this is the not gate, this is the and gate, this is the, whoops, that's a not gate. And then this is an or gate, okay? Not, I'm just making sure I got it copied right before I screw things up. Okay, so how does this go? You can kind of see that these two guys are attached by this and. So it's going to be a not P right here and Q right here. Okay, so the result of this gate is going to be not P and Q. All right. Then when you go for this Q, you'll have not Q resulting. So Q will go into here and become not Q. And then finally, you're just connecting these two with an or. So you'll have not P and Q, or not Q. Okay? You use the parentheses to indicate that these guys are grouped together. Let's do one more of those. So part, I don't know, C, no, part B. So this time we have P, Q, R, S, T. As usual, I apologize for running off the page. I need a better webcam one of these days. So hopefully I won't have to teach online. Well, teaching online is all right, I guess. P and Q, so we have an AND gate here. And then we have an AND gate with R and S. And then these guys are going to connect together with an AND gate. And then these guys, T is going to connect up with these guys at an AND gate. Okay. Okay, so first off, P and Q right here. Right here we have R and S. And then this gate connects these two guys together. So we can use parentheses, P and Q, and R and S. Right. And then from down here we have a T coming in, so we have a T. And then it's all of this in parentheses and this T. Okay, so we have then P and Q and R and S and T. Okay. Okay. It's not a bit. It looks cool, you know, but once you get the hang of it, it's like, okay, this is no big deal. Let's look at the next type of conversion that we need to do. This time we're going from the other way around, right? We're gonna start with the statement form and then go to the circuit diagram. In other words, go from the Boolean expression to the circuit. All right. Okay. So number 13 is given. Let's make sure that's the right problem I want to look at. Sure. So construct the circuit for the Boolean expression. We have not P or Q. Okay, so we have inputs P and Q. And then I need a not P, so I'm going to have a not gate. And then we'll connect that in with Q via an OR gate. Right, so our OR symbol counts like that. And then our output to whatever. We call it R or something. Let's try another one. So number 15. And we have P or not P and not Q. Okay, so I need a P and then a Q. So first off, there's I'm ORing it with this nightmare. Okay, so I need a not Q or not P here. Let's put a not P here. I also need a not Q. And then these guys are being connected together with an AND. So I'll just do it like this. And then I'm connecting these ties together with a P. So I'm going to need to kind of solder in another wire right here for this P. Make him go down here. And then we're doing an OR. Okay. And then it goes to your output. And there it is. Okay, I don't get too crazy about maybe there's a specific way you always have to make these go down or something. You never want to cross wires. I'm not going to get carried away with anything like that. And maybe it's like a graph theory problem or something, it seems like. Yeah, I've not been taught like a particular way of laying down the circuits. Just do the best you can, and it'll never be an issue where you have to actually physically draw one on the homework. They usually give you like choice A, B, C, or D, and they'll all be drawn for you. All right, let's look at now creating a circuit from an input-output table. We're going from a truth table to a circuit diagram. So input-output, input-output table to the circuit diagram. And so how does this work? It's pretty simple. If you just follow the basic program, you'll identify all the outputs of one. So you're looking at the final column and you're identifying the rows with outputs 1. Then you create a conjunction based off of those rows. And then thirdly, you'll create a disjunction of those particular rows with outputs of 1. It'll be more obvious once I show you an example, but create a disjunction of rows. Okay, so let's look at number, I guess, 20. And you have this big table. And it's not really that big, but P, Q, R, and then the output is S. Okay, we populate P, Q, and R in the traditional manner. So 4 ones, 4 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, and then alternate 1 0, 1 0, 1 0, 1 0. And then this final column is given to you. It's not like you're using any sort of conjunctions at this point. It's just, it is what it is. Okay, so the output column is given 1 0, 1 0, 0, 0, 0, and then finally another 1. Okay, so now let's go to this program and hopefully it'll make more sense. So the first step is to identify outputs of 1. Okay, so there are 3 outputs of 1. There's 1 here, 1 here, and 1 here. From each of those rows, you're going to create a conjunction based on those. Okay, so how do I make this conjunction? And conjunction, it should have ands in it. You're going to go P and Q and R if they're all ones. If you have a 0 involved, you'll go not that. In this case, we have ones for P, Q, and R, so we're going to write P and Q and R. If you have a 0, you're going to write not whatever that variable is. Okay, so in this case, we're going to write P and not Q and R. Okay. So the result of this statement with these truth values would be a true value, right? So if I put in 1 and not 1 is not 0 will be 1, and then this will be 1. 1 and 1 and 1 will give you an output of 1. Okay? So if you have a triple conjunction, all 3 of them have to be 1s for it to be a true value, or in this case, a 1. All right, so down here then, you want not P and not Q and not R. So not P and not Q and not R. And then the end, what I say, the third part, create a disjunction based off of these rows. So you'll have a true statement resulting, or you would have an output of 1 if you have either this true, or this true, or this true. And that's a disjunction. That statement I just made is a disjunction. So you'll have a true value if P and, you'll have a true value if P and Q and R is true, or if you have this other one, P and not Q and R is true, or you have this guy, which will be not P and not Q and not R. Okay? So you get that big, long, nasty looking thing. And we can then convert that into a circuit diagram. Okay, so here we have our Boolean expression. Now we want to go to a circuit diagram. Okay, so this may take a little bit of paper. It's typically not going to be all that pretty, but like I said, in the computer, they'll have it drawn for you, and you're just picking A, B, C, or D. Okay, but let's see if we can do it brute force, right? So you have P, Q, and then R. Sorry. Okay. And then I need, at the end, I kind of go backwards. At the end, I need there are 3 and statements that I need, right? So I'll have an and, an and, and an and then we take these 3 and we make a big OR gate up, send them into an OR gate, right? So these guys will get sent into an OR gate, like that. Okay, and then we have 3 inputs on each one of these. 2, 3, 1, 2, 3, 1, 2, 3. Okay, and I'm going to have to cross my circuits probably somewhere here. Okay. So first P and Q and R. So P and Q and R. The second guy is P and Q and not R, so P. And this is where I'm going to have to sort of cross. So I'm going to do it like this. So just leave a little space, like one underneath. P and Q. Well, it's not Q, right? So I need to send this circuit here into a NOT gate first. And then I could send them to this conjunction gate. Right? And then and R. Okay, so I can do R here. I don't have to cross any circuits. And then finally, I need NOTs on each of them. So I need to hit these guys in NOT gates. So he's going into a NOT gate. And then I'm going to, yeah. He's going to go underneath here. Oh my gosh. Yeah, sorry. I hope I'm not butchering this. Any real engineers know how to do this. I apologize. But there, he's going there. What else? I need another NOT Q. Okay, so I could probably solder onto here or just do another gate for the NOT Q. And then I need a NOT R. Okay, something like that. I am by no means an engineering type, electrical engineering at all. I never even took the digitals class, but that's the idea. Okay. So obviously this thing is a very complicated looking character, and it'd be nice if we could simplify this expression significantly, and then we could simplify our circuit so it wouldn't be such a nightmare, right? Right. So we could do that then using our equivalence statements. So De Morgan's rule, identity rule, all that stuff. We could use that to simplify, right? So equivalent circuits now. So section, I think it's 8, equivalent circuits. And let me get my theorem so you can follow along. This is from section 2.1. It's theorem 2.1.1. We'll be needing this stuff. Okay. Okay, so equivalent circuits. So 31, they give you this mess of a circuit, and they're hoping you can rewrite it. So we have not P and not Q, or not P and Q, or P and not Q. All right. Okay, so it looks like I could do some sort of distribution with these guys, these not P's, and pull them out of the first two parentheses. So we can say this is equivalent to not P and not Q or Q. And then or P and not Q. So that's distribution. Okay. Either I'm alive or I'm dead. This thing is a tautology. You actually have to do a commutative law first, but let's skip that. Okay. We'll say not P and it's a tautology, or P and not Q. Okay. So this was called the negative law. Let me look. Q and not Q. It's this thing right here. Yeah, negation law is what they're calling it. Okay, and then this portion right here, this not P and T, is an identity law. That's just going to give you not P right back. So that's identity. Okay. And then it looks like we can do another distribution in the other direction. So I'd end up with not P or P, and not P and not Q. Okay, so that's distribution. And again, we have this kind of identity, this time tautology. Oh, it's another, I'm either alive or I'm dead, right? So that's another tautology. T, I should use a commutative law first, but I'm just going to skip that. Oops. Lowercase q there. So this is, what do we call it? Negation again. Okay, and then if I have something and a tautology, just like I had up here, it's the identity. You just end up with this part. It's like multiplying by 1. That's why they call it identity, right? The multiplicative identity. So you're just going to end up with not P and not Q. You should, again, they want you to do another commutative law first to get the T on this side, so it looks like it's exactly in the form that you have in the book. And that's what you would need to do if you're writing a computer program, because typically, I guess, a computer wouldn't be able to tell via some sort of direct substitution that was true. You know, they can't tell the difference between 1 plus 2 and 2 plus 1 or something. I don't know. If you read that thesis on the logic theorist, again, which I mentioned before, is it called the logic theorist? They write a computer program in that thesis which does all of this sort of simple logic. Okay, so anyways, our objective here is to write this circuit with as few gates as possible. And we can now do De Morgan's in reverse and pull out the negation and have just 2 connectors. Okay, maybe you would argue the parentheses are connectors, but it'll be not P or Q. And we just have these 2 connectors. Okay, and that's De Morgan's. Okay, there's also the NAND and NOR gates in the book. I don't think they come up in the exercises, though, so I'm just going to leave those to you. And if they do come up the exercises, you know, go read the book. It's in there. And you should be okay for the homework, though. Okay? Okay, we'll see you next time.